and the products can react with each other to give back the reactants. That is called the reversible reaction. We can take the example here of the dehydration of copper sulfate crystals. Basically, copper sulfate crystals can exist in two different states. It can exist in the form of the hydrated and in the form of the anhydrous form. When it is in the hydrated form, then the color of the copper sulfate is blue, and when it is anhydrous, it shows the white color. So on the basis of the color of the hydrated and anhydrous form, we can know that the reaction is going either in the forward direction or in the backward direction. When this salt is heated at a high temperature, the water will be removed from the hydrated compound, so it will convert into the anhydrous form, and you will see a white color, a white solid material in the beaker or test tube wheresoever they have put the salt. You will see that the gases will combine with each other again. Ammonia gas will again join with the hydrochloric acid on this end of the test tube, and they will again form the NH4Cl, the white solid. So the ammonium chloride is now produced on the open end of the test tube, whereas it is heated in the bottom end of the test tube. Is that clear?
Yeah.
Okay. Any question?
No, I understand.
All right. Then we have the reversible reactions in a sealed container. The reversible reaction in sealed container, it is not very much explained properly here. In this book, I need to explain this topic from the other book for proper explanation. We have just discussed this reaction in which we were saying the conversion of ammonium chloride into its constituent gases, the ammonia gas and the hydrochloric acid. Now about the equilibria. Coming to equilibrium, whenever we have a certain type of the reaction in which one thing is changing into another thing, then that will be considered as one way direction of the chemical reaction. For example, if we say that we have an ice and this ice is being heated, then it will be converted into the water. The ice is converted into the water, and when we decreases the temperature, then it will go back to the ice form. In our observation, we will see that 0 degree centigrade is considered as that temperature in which both the ice and the water states are coexisting with each other. They coexist, which means they both are occurring in this temperature. So this temperature in which the ice is being converted into the water and the water is being converted back into the ice, this type of the temperature is considered as this type of the reaction, or this stage of the reaction, is considered as a equilibrium stage. The equilibrium stage in which both the forward and backward reactions, they are occurring at the same rate. This is forward represented by F, and this is backward represented by small r. So in this case, both forward and reverse reaction are being happening. Is that clear?
Yes.
Okay. When equilibrium is reached in any reaction, the amounts and the concentration of the reactants and products do not change anymore. However, both the forward reaction and the backward reaction is still going on. So what is the property of the chemical of the equilibrium? What is the property of the equilibrium reaction, it is that the amounts of the reactants and the products do not change anymore, which means whatsoever amount of the water has been formed, it will remain the same, and whatsoever amount of the ice has been formed, it will remain the same. They will not change, they will remain the same, but direction of forward and backward direction will still go on, they will not stop. Is that clear?
Yes.
Okay. We can also apply it for the nitrogen gas and the hydrogen gas. When nitrogen gas and hydrogen gas react with each other, they form the ammonia gas. We can again apply the same principle of the equilibrium on this reaction, that if the nitrogen and hydrogen are reacting, they form the ammonia, and the ammonia gas can still decompose to reform its constituents nitrogen and the hydrogen gases. These are the two processes being carried out at the same rate: the formation of the ammonia gas and the formation of the nitrogen and hydrogen gas by decomposition. The amount of the ammonia gas, let's suppose if we say that almost 3 moles of the ammonia gas is formed as a result of the reaction by nitrogen and hydrogen, and we also say that uh, 2 moles of the nitrogen gas and 2 moles of the hydrogen gas are present in the equilibrium. The reaction is in the equilibrium stage, and the 3 moles of ammonia is present in the mixture, 2 moles of the hydrogen gas is present in the mixture, and 2 moles of the nitrogen gas is present in the mixture, and the reaction is carried out in both directions. So the amounts of the gases will remain the same, they will not change. There will always be these much moles of the nitrogen gas, hydrogen gas, and the ammonia gas in the mixture. Is that clear?
Yes.
Okay. I can show you the graph which is related to this type of the reaction. This is a graph which indicates that the reaction of both forward and backward. Do you know that whenever we have a graph for the reactants, then we will plot a graph for the reactant in this way. The amount of the reactants keep decreasing as the time passes, and it will reach to a certain limit, after which it will become horizontal, right?
Yes.
This is the graph to represent the amount of the reactants. The y-axis indicates the concentration. This is the amount of the concentration, and the x-axis represents the time. As the time passes, the amount of the concentration, we can also say it as the amount, or we can also say it as the concentration. The concentration or amount of the reactant falls as the time passes. And for the products, we'll plot a graph like this, in which the amount of the product is increasing, and then it reaches to a certain point, after which it becomes horizontal. So here this graph indicates the amount of the product as the time passes. So we can conclude from this type of the graph that this point on this graph, where the both lines have reached the horizontal lines, after this point you can see that both the graph of product is horizontal and that of the reactant is also horizontal. This point means at this time the equilibrium is reached. Equilibrium is reached at this point. Is that clear?
Yes.
So that's how we can indicate the formation, we can indicate the graph for the equilibrium reaction. The example included in this topic is not very much clear because it all says about the blocks present in the large size block, so it is not a very good example. But the overall summary or the overall idea is that the amount of the products and the reactants remain the same when the equilibrium is reached. And what is meant by the dynamic equilibrium? Hmm?
I'm not sure.
Have you got the idea of equilibrium?
Yes.
Okay, dynamic equilibrium means that the reaction occurring from reactants to the products and from products back to the reactant will still go on. It will not stop. The reaction from reactant to product and from product to reactant, or in other words, you can say the reversible reactions. The reversible reactions are still going on. They are not stopping. So as a result of this reaction being in always in dynamic state, they will give you the equilibrium situation. The dynamic reactions is giving the equilibrium position or equilibrium situation. So the reactions are not stopping, they are still going on, and as a result of these reactions being carried out, you are getting the equilibrium stage. That is called dynamic equilibrium. Is that clear?
Yes, it's clear.
All right. Basically, the dynamic equilibrium is the complete name of the equilibrium. And one thing another about the closed sealed container here. What does the sealed container means here? They were explaining this topic sealed container. What does it mean?
Now there's like no other substances present, like only the reactants that are needed are there.
No other substances are present, like only the reactants and the products are present.
Yes.
Yes, exactly. They are saying that if this is a sealed container, then within this container the reaction between reactants and products is being carried out, and no other substances is being added from the outside, or no substance is being escaped from the container. So nothing is coming in and nothing is going out. That is called the sealed container reaction, or the reaction within the sealed container. So only the amounts of the reactants are and the products are present within the sealed container. Okay, now moving to the next part, that in the dynamic equilibrium the rate of the forward reaction is equal to the rate of the backward reaction, like by which amount the by which rate the amount of the reactant is decreasing, and by which rate the amount of the product is increasing. That is called the rate of the reaction. And they are taking an example of the calcium carbonate. Calcium carbonate, when we heat the calcium carbonate, then it converts into the solid form of the calcium oxide and the gaseous form of the carbon dioxide. This reaction is supposed to be carried out in the sealed container, because if we would say that the container was not sealed, then definitely this gas would have escaped out of the container, and when it would have done this, it will be eliminated from the whole mixture. So in that case, this will not be considered as an equilibrium reaction because the carbon dioxide has already been removed, which means nothing, no reaction will be occur in the reverse direction, in the backward direction. For the reaction to occur in the backward direction, then we would need the carbon dioxide in the mixture. So for that purpose, we will always consider that the reaction is being carried out in the sealed container. Is that clear?
Yes.
All right. Now the position of the equilibrium. We have just seen that A to B means forward reaction and from B to A means backward reaction. But what about the position of equilibrium? Position of equilibrium means that in which direction the reaction is most occurring, in which direction the more substances are present. That is called the position of the equilibrium. Let's suppose if we have A and if we have the percentage of A as 90% and the percentage of B as 10%, it means that more amount of A is present in the mixture. Although the reaction is equilibrium, which means both the reactants and the products are present at the same time, but the amount of the reactant, this can be considered as a reactant if we move from in the forward direction, and this will be considered as a reactant if we move in the backward direction. So I cannot say it as reactant and product. I have to name them because only then you will understand to which substance are we referring to. Is that clear?
But how would the percentages be different if it's in a sealed container and the reactant and product side are always equal?
Basically, the amount has nothing to do with the equilibrium. The percentage is basically that how how much of the A has been decomposed. Let's suppose if I take the initial case, for example, I had 100% amount of A substance, 100%, and in that time there was how much amount of the product, or the how much amount of the B were supposed to be present in that case. Hmm?
What? Can you repeat your question?
I'm saying if I take it back, if I take it a little while back, in which I would say that A was present by 100%, then how much amount of the B would be present in that case?
Also 100%.
No, they will be 0%. You are getting the
How
point.
do you 0%?
See that this 90 plus 10% means how much? 100%. This 100% is being contributed by both A and B. But if I give a total 100% value to A, then how would amount of B will be there?
Oh, okay, yes,
Nothing.
understood.
There will be nothing. So it means that the reaction was started from this stage in which A was 100% and B was 0%. But after a while ago, after some time was passed, then the amount of A reduced to 90% somehow, like because the reactant has to react with each other to form the product, so that's why the amount of A reactant will decrease. So it has reduced to 90% and the amount of the B has reached to 10%. Now this is the time when we will say that equilibrium was attained. It means you do not mean to say that the reactant were supposed to be 50-50 each. It doesn't mean that A should be 50% and B should be 50%. That is not the requirement of the equilibrium. The requirement of the equilibrium is that both the reactions are occurring at the same rate, but it doesn't mean that their values are same. Is that clear?
Yes, it's clear.
So when the reaction has reached the equilibrium, there were 90% of A and 10% of B. Now the equilibrium was achieved. This is the equilibrium stage. Okay, now you can see here clearly that the amount of A is more than B. So for this case we will now use the concept of position of equilibrium. The position of equilibrium means in which direction is more favorable, or in which direction there are more amounts of the substances. So here in this case, in which direction or of which substance do you see the more amount?
In A.
In A. So we will say the position of equilibrium lies to left side, or you can also say, if you consider it as reactant, it and this as product, you will also say that position of the equilibrium lies to reactant. That's what it means. The one which carries more amount, in that direction, that side is considered as a more favorable position of the equilibrium. So the equilibrium in this case lies to the left side or lies to the reactant side, or you can also name it as lies to A side. The name of the substance lies to A, or if we're supposed to be any other example, let's suppose ammonia. If A was representing ammonia, then we will say position of equilibrium lies to ammonia. Is that clear?
Yes.
Okay. So that's how we say about the position of the equilibrium. Now there is another example in which A is still 80% and B has now changed to 20%. Now what happens here? We say that the position of equilibrium has shifted. It doesn't matter that we will still have more A. If we compare this, if we compare this case with the other case, if we have to compare these two together, then we will have to explain about the position of equilibrium in the second case. When we compare the second case with the first case, we will say that the position of the equilibrium has shifted to the right. Position of equilibrium has shifted to the right. Why? Because more amount of the B is being produced as compared to A. More there is an increase in the amount of B. The one which shows the more increase in the amount will indicate the position of the equilibrium. Is that clear?
Yes.
For the first case, we did not compare it with any other case. We were just looking at only one reaction in which there was 90% amount of A and 10% amount of B. So we said that A is more, which means the position of the equilibrium is towards the reactant A or towards the left side. But when we compared this with the other case, we saw that A was reduced about 10% and B was increased by 10%. So we said that the position of equilibrium has now shifted to the product B or towards the right side. So that is how we express the position of the equilibrium. Is that clear?
Yes.
Okay. The next topic is based on how to predict the effect of changing conditions on the position of equilibrium, and in this topic we have different factors like changing the pressure, changing the temperature, adding the catalyst in the equilibrium direction. So I think I should start this in the next class. What do you say?